Yeah, so hi, I'm Robert Clifton-Everest. So this work is on streaming irregular arrays. So this is something that came up when we were trying to actually implement audio compressor using a GPU. So I'm going to give you a very sort of high-level overview of what we were trying to do. So this is what it will look like. We have in our CPU, in the CPU memory, a continuous stream of audio we want to process. What we want to do is take chunks of the audio, transfer it to GPU memory, process it in the memory so that we get out a series of small matrices, then transfer those matrices back to CPU memory. We have to be careful here though, because if we transfer too small a sample, we're not really exposing enough parallelism in the processing in order to actually to saturate all the cores of the GPU. If on the other hand, so this makes us unhappy, if on the other hand, we want to transfer even more data, we may transfer too much, in which case you exhaust the available memory, and this makes us really unhappy. So we have to be careful here. We have to make sure that we pick a sample size that's just right. This makes us happy. So the two problems we had here was, first of all, as we saw, that we have to be very careful about the size of the memory we process with. We have to be careful how we chunk it up to make sure that size both fully saturates all our cores but doesn't exhaust memory. This is a factor that depends on the nature of the hardware. If we were to swap out for a different GPU or even a CPU, that number could change. The second problem is not so obvious. But we have an essence of irregularity here. Because we're producing a series of small matrices, they may be small, but they're all of different sizes. So we need some sort of an irregular structure to store them in. We need a data structure that supports storing elements of different size. And this is of particular complexity when we're dealing with GPUs. These are both more general problems. They don't just occur in this example. Anytime you have more data than fits in your GPU memory, you have the first problem, which is quite common, and anytime you're working with data which needs to be represented irregularly, you have the second. So the question we're trying to answer with this research was, can we solve these problems using a high-level language? Is it possible to, using a high-level language, to abstract away from these concerns? So can we abstract away from things like how parallel the hardware is and how much memory it has? And also, can we abstract away with how to best represent these sort of complex irregular structures? So, more concretely, could we do this in a language like Accelerate, which we've developed at the University of New South Wales? So Accelerate is a data parallel language. It features combinators that would be very familiar to most Haskell programmers, like map, fold, zip width, and scan. But it works over sort of these regular n-dimensional arrays. So they're arrays of fixed dimensionality, and it doesn't support nested arrays. Very conveniently for us, it also supports multiple targets, so it can compile code for both GPUs and CPUs. Would make our solution more portable, but not only would it do that, it would mean we could actually allocate different parts of our solution to different processors. So we could do the first part of the compression on the CPU and then the second on the GPU, or vice versa. So how well does it actually address the problems I brought up? So firstly, does it allow us to constrain the memory usage? Well, not really. Because Accelerate is an array language, and many of its combinators assume a random access to the array. Many of the combinators can be used to sort of permute or change the order of an array, or they can also be used to index the arrays, and that's necessarily a random access operation. So for that reason, the way Accelerate has to work is it has to load the entirety of any array it is working with into memory. So this is a problem for array languages in general, that they sort of assume you have all your data there and can fit into an array, which may not be the case if there's just too much data, or if it's just not there yet, if you're streaming in over a network or something. So we do have a solution to this problem, though. In our previous work, we introduced the notion of a sequence. So this is a structure, in addition to an array, that but only allows linear access. So it only supports a limited subset of the operations. So it can do things like map, zip width, and fold, but it can't do any sort of permutation, nor does it allow for any sort of arbitrary indexing. So with this limited structure, we can now approach things more differently. So because it's limited in this way, it doesn't have to be loaded into memory all at once. It is now up to the compiler, or the runtime system, in fact, to decide how to process it. The runtime system can decide how much of the sequence it wants to process at once. So this does give us a solution to the first problem. The second one, however, is more complex. Because Accelerate works over regular arrays, it doesn't offer a really convenient way of working with irregular data, like this series of small matrices. There are, however, solutions to that. So other languages support what we call nested parallelism. So that's languages like Nestle or Data Parallel Haskell. These are languages that support irregular nested arrays. So the arrays can have elements of varying size. You have arrays of arrays. So this is particularly useful for things like sparse structures, like sparse matrices, and other sort of complex sparse trees. But the downside of these languages is that they assume irregularity. They treat all nested arrays as if they are irregular. So they assume that all nested arrays may have elements of varying size. This is not always very efficient. For example, supposing you're doing a zip width over two irregular arrays, this is a non-trivial operation because, in part, the size of the output is not easily calculable. You have to actually look at the size of all the rows in this matrix in order to figure out what the actual size of the output is. So for that reason and a few others, working with irregular data carries a cost. And if your data happens to be regular, then it doesn't offer any great benefit. So what we would like to do, going back to our example, is say, okay, let's treat it this way. Let's write a program that takes in a sequence representing the audio stream we're working with and produces another sequence as a result that represents all the matrices of the output, so all the matrices that represents the compressed audio. This program is going to have some intermediate sequences in order to do its work, and some of those sequences may in fact be regular. So some of those sequences, all the elements will be the same size. And we want to make sure that we can get maximum efficiency there. So if they all happen to be the same size, we're not necessarily having to pay the cost of working with irregular structures. More concretely, our aim in this work was to support both regular and irregular sequences, but only pay the cost of irregular sequences when they definitely are irregular. So what we want is to not necessarily assume irregularity in the same way that the nested parallel languages did. So how did we do this? Well, we had to address a few problems, and the first one we'll look at is how to actually represent the data in a sequence. So sequences by their nature are chunked up. So how do we actually represent a single chunk of that sequence for processing? In the simplest case, suppose we have just a chunk of matrices that are all the same size. So we had a sequence of matrices. We take off a chunk, which is 4 matrices. How might we actually represent that? Well, what we do is we take those matrices, we concatenate them together, and then just treat that concatenation like a 3D array. This is a representation that fits very nicely within Accelerate's flat data parallel model, and other languages' flat data parallel model, and is very easy to work with. The more complex case comes when we have an irregular sequence. So suppose we pull off a chunk off our regular sequence, and this sequence we also get out 4 elements. What we have to do here is, well, for starters, we concatenate all the elements again, but this time we also have to store some additional information. This additional information is the segment descriptors. These capture the size of all the matrices in the chunk separately. So this representation has a bit of an overhead in terms of what it has to store, and is potentially more costly to work with, but it can represent this irregular sequence. So what we have here is, given some sequence of where the elements are unknown, we have the regular possible representation, but also an irregular possible representation. We can sort of view this as like a system of surface and representation types. But instead of a function mapping surface types to their corresponding representation, we have a relation. So with these two representations, how might we work with them? Well, let's do an example. So suppose we have this function here. This function just simply takes a matrix and sums along the row of each matrix, producing a column. If we take this function, and suppose the programmer says, okay, I want to apply this function to every element in my sequence, a sequence like this, what they will do is say, okay, apply the function. From their perspective, what they want to happen is something like this. It just reduces down to columns. What's actually happening behind the scenes, though, is we take our representation of that chunk and we use a slightly different version of the function. So this version of the function is generated by the compiler. It's been vectorized into a regular vectorized version. So this version is able to work over this 3D array. And so it looks like this. Okay. In the case of applying this to an irregular sequence, though, so we do the same thing. We apply the function to every element. From the programmer's perspective, it should look something like this. But in the underlying version, what's happening is we've got our segmented representation with the segment descriptors, and the compiler generates an entirely different version of the sum rows function that works over this irregular representation, like so. Our story so far is that we have two different representations. And we can generate code for either one, so the programmer doesn't have to write the code to work with these representations. It can all be hidden under the hood. The only real question left is which one to use. So this is something we would like the programmer not to have to deal with. The programmer shouldn't have to just know up front whether their sequences will be regular or irregular. It should be able to just apply functions to them, and the correct version should be called for them, and the correct representation used. So we really want our compiler to not only be able to vectorize our functions so that they can work over these representations, but also choose which representation to use at the appropriate time. So that's what we did in our work, and I'm going to show this by example. So I'm going to assume we have a very simple function that takes two matrices as input. One matrix, it applies a map to it. The other one, it applies a filter. It then takes those two results, combines them with a zip width, and then folds the result of that. So this gives us sort of the general shape of the function. What needs to happen in order to apply this to a sequence, if we want to apply this function to every element in a sequence, we need to vectorize it. So if we start by, say, assuming, okay, that we'll assume we're applying this to two regular sequences. So we're combining two regular sequences by using this function. In the case of the map, we're applying a map to a chunk from a regular sequence. Well, map doesn't change the size of its input. It results in the same size. So therefore, map is regularity preserving. So if you apply map to an already regular sequence, you're going to get back another regular representation. So we go from regular to regular. With the filter, though, because the size of the filter doesn't depend on the size of the input, it depends on what's actually inside it, we can't know what we're going to get out at the end. We don't know that it's still going to be regular at the other end. So as a consequence, at that point, the compiler will choose to use the irregular representation. With the zip width, we're combining both a regular and irregular structure. So as a consequence of that, it has to still be irregular. So this entire function, when vectorized, it can be used to process two regular sequences. But what it will produce at the end is an irregular sequence. So that means that if we apply this to our entire computation, we can sort of right from the start, as long as we know right at the start whether it's in a regular or regular sequence, then we can infer it all the way up. So this is not, of course, the full story. In order to also, for many other things you have to do to implement sequences, we also have to deal with scheduling. So that's how to actually decide dynamically the chunk size of elements to process. But also, we have to implement things like vectorization avoidance. And that is to avoid vectorizing in the cases where we don't need to, which is very important for performance. In addition, we had to extend our existing fusion framework to deal with the output of vectorization. So vectorization produces code which is typically hard to fuse, and we had to extend our fusion framework in order to sort of better handle those cases. The details of all of that are in the paper. So the real question is the results. How well did this actually work? Well, let's look at our audio compressor example and see how it did. So this is a strong scaling graph. So that means higher is better. So this was we did this on a dual socket machine with two 12-core CPUs. That distinction is necessary. We'll start with what happens if we just did this in plain accelerate. So this was a version we wrote in just plain accelerate without sequences. So because it was written in plain accelerate, we kind of had to process only a matrix at a time. We couldn't process matrices in bulk because we didn't have a way to sort of vectorize working with multiple matrices at a time. So what you can see here is it scales okay up until about 8 cores, in which case it starts to sort of waver a bit. There's a couple of spikes there at 12 and 24 cores, but for the most part it starts to flatten out a bit more. Applying our sequences extension, however, in this case, we're able to process many matrices at a time because we've got vectorization, so we were able to write it much the same way, but due to automatic vectorization, we were able to process many matrices. As a consequence, we were actually able to saturate many more of the cores on our CPUs. And as a consequence, it scales much better. As an additional benchmark, we also did sparse matrix vector multiplication. So in this case, we compared our solution with plain accelerate as well as the Intel math kernel library. So starting with plain accelerate, as we can see here, this scales not great, but scales reasonably. When we applied our sequences extension, it didn't quite perform as well. And so the reason for that is, in this case, the plain accelerate version was hand vectorized. So we actually had to write a hand vectorized version rather than relying on automatic vectorization. But the sequences one was automatically vectorized. So as you can see, that does carry a slight cost in this case. There was a slight cost to that automatic vectorization, and also an additional overhead due to the using sequences with scheduling. But it's not so bad. And in fact, when we compare it to the Intel math kernel library, we're still relatively competitive. Okay, so in the paper you can see other benchmarks as well. So in summary, we were able to extend our existing array language with sequences to enable us to work with larger data sets that don't necessarily fit in our GPU memory. And this also enabled us at the same time to express more sort of complex nested and irregular computations, which are typically hard to do on GPUs, and any other array languages as well. And most importantly, we only had to pay the cost of that irregularity when we needed to. We were able to, for the parts of our larger example that was purely regular, we didn't pay any cost of that irregularity. Thank you. So it should happen seamlessly. So the programmer doesn't even really need to know. Obviously, at some point, it depends on how they introduce their data. So if they've introduced their data by saying, OK, taking this array and then slicing it up into a sequence, we know that's going to be regular, so we'll infer that, and that they don't have to worry about that. If they're introducing their data in some other weird way, they may have to say, yes, this is irregular, and they've introduced it. But then from that point on, we've inferred any regularity or irregularity along the way. Mm. Yes. So if you as the programmer know that what you're giving it is regular, then you can assume that yes. Until the point you start using things that make that data irregular, it will be treated irregular, yes. Yeah.
So one, your example earlier was filter and the map. But there's an example of something where you don't know anything about the output, so it could be regular or it could. What do you think could you over-allocate efficiency?
It can depend. So the way we do filter isn't necessarily that efficient, so we don't over allocate. So we're deliberately, we do multiple passes. We do one pass to figure out how much space will be, and then the second pass to actually do the so. Yeah.
Okay.
Yeah.
So it seems like from that same example, when you combine regular and irregular data structures with these operations, then the output is always irregular. So is there any way to recover regularity?
It can happen, yes. So there are ways that does happen. There's not many simple cases where that, but you can construct programs that will sort of take in something irregular and ultimately result in something regular. If you do like a fold, so this is kind of if you've got like a sequence of arrays and you fold each one of them, what you end up with is a sequence of just single elements. That's obviously regular. Yeah. So there are cases like that.
Is that modeled?
Yes.
Okay.
Yes.
What if you have an operation like a filter for which the output just happens to be regular?
Then we can't model that. We can't infer that in any way. In some ways, I guess you could, but yeah, we don't try and do that. Okay, so yeah, that is quite a complex question, and there is more detail in the paper. But so our streaming constructs are very limited, very, very limited. So in fact, we don't have to buffer at all. So there's constructs that way that we are very limited. So essentially, you have you can map over a stream and you can reduce a stream, but that's about it. And we don't try to do anything fancy with buffering. In terms of the rate control, the details are in the paper, but we have a very basic scheduling method that says, okay, just try processing this much. How much have we got reasonable CPU? Have we got reasonable utilization? Let's try increasing it, see if that improves it, and then just sort of decrease it if it doesn't, and things like that. So, yeah. It's pull. It's a pull situation. So we're assuming it's a pull situation. Yeah. No. We've not done anything like that. We've not tried to hook it up to any sort of external sources. Our ability to sort of connect this with any sort of external data sources at the moment fairly limited.